here we've got this piston cylinder assembly again, and it's got 20 cubic feet of air at a temperature of 600 and a pressure of 100 psi. It's going to undergo a polytropic expansion to a final pressure of 51.4 psi. Now the process follows this equation here. So P times volume to the power of 1.2 equals a constant. Work is going to be a positive 194.34 BTU. Now we're going to assume an ideal gas, so that's going to be important here. And we're going to neglect kinetic and potential energy effects. We want to find mass of the air and the final temperature. And we also want to find the heat transfer in BTU. So let's go ahead and get started. Let's find the mass of the air first. It told us we have an ideal gas. That means we can write the expression that mass equals P1 times V1, where this is volume, over R times T1. Now we have all of these values. R you would have to look up in the table if you weren't given that. So we can plug everything in and then check out the units. So pressure is going to be 100 psi. Temperature, volume, is going to be 20 cubic feet. That's going to go over R. Remember, R is R bar over the molecular weight. R bar in this case will be 1,545. Molecular weight is 28.97. And the units you get from that are foot-pound force per pound degree Rankine. And then our temperature is 600 degrees Rankine. So we got that. Now our mass needs to be in pounds. So if you look at these units, they are looking fairly decent. But we have this inches here. We need to get rid of this inches. All right, so let's get rid of that. And those pound force goes away. So let's just multiply this thing by 144 inches squared per foot squared, and then that takes care of the inches. And then that will also help us get rid of the feet. Okay, so now you got that. Now, once you solve for M, you're going to get 9 pounds. So there's your first answer. Now we also want to find the final temperature. Now we have this polytropic relationship given to us. We know that PV to the 1.2 equals a constant C. We don't know what V2 is. We know the final pressure. We do not know the final volume. So we need to find that final volume. So using this, we could then write P1 V1 to the 1.2 equals P2 V2 to the 1.2. And we want to solve for V2. So V2 then is just going to be P1 over P2. Exponent here is 1 over 1.2, and then multiply that by V1. Now you'll just need to plug in your values. P1 is 100. And these units for pressure will cancel, so I'm not going to write them out. And then P2 is 51.4. And then V1 was our initial volume. That was 20 cubic feet. Alright, so now we have that. So this means V2 is 34.83 cubic feet. Now we have that. We're still looking for our final temperature. Now you're going to go back to that ideal gas law, and using that we can write that the temperature at state 2 is equal to the pressure at state 2 times the volume over the mass times R. So essentially we just restructured this equation from what we had up here. Now we have everything we need, so you can go ahead and just plug in your values. And then you'll have to check out your units again, make sure you have them all right. Pressure is going to be 51.4, volume is 34.83, and then you put it over the mass, which is 9 pounds, and then R is going to be what we had up here, So the 1545 over the 28.97. And again, that's foot-pound force per pound degree Rankine. Now again, here you're going to have to get rid of the inches squared. So let's do 144 inches squared per foot squared. Now if you look, once you do all of your units, everything's going to cancel out except for degrees Rankine, which is what we wanted. So all this stuff goes away. You're left with this degrees Rankine right here. So T2 is going to be 537 degrees R. So that'll be our final temperature. Now what we need to do, we need to get heat transfer. That one, remember, you're going to use energy balance. Anytime you want Q, just go to that energy balance equation. And we already said kinetic and potential terms are going to be left out, so I'm not going to write them out. That's going to give us delta U equals Q minus W. Now, we got to use the table here. So we need specific internal energy, so let's rewrite that. Remember, delta U then is going to be M times U2 minus U1. These are the little u's. These will be the ones found in the table. Then that gives us Q equals M times U2 minus U1 plus work. Now for these two, you're going to go to the table. You're going to use your temperature that you have. So your initial temperature was 600, your final temperature was 537. So for U2, what you're going to get, that's our, let's put the temperature here. So that's at 537. That's going to give you 91.53 BTU per pound. That's what you'll get in the table. And then if you look up U1, which is at a temperature of 600 degrees Rankine, you're going to get a value of 102.34 BTU per pound. Now you can just take those values, plug them in here. We already know the mass. Q is going to be 9 pounds times the 91.53 minus 102.34. So BTU per pound plus 194.34 BTU. And that's going to give you 97.05 BTU. Now this value is positive, so just like this picture shows, you've got energy transferred by heat into your system. Your work was positive, so you've got work being done by the system, so you can transfer energy from the system to the surroundings.